It's time for us to do some practice involving area and polar coordinates. A lot of it is just sitting down, getting the setup right, and trigonometry. Wow, trig! Sounds like wonderful times. Back to our old trig classes day. We love trigonometry, don't we? Of course we do. So it's important to do practice, and of course if you're following along with the video, make use of the pause button. If you see a problem, pause it, try it out, see how you do. If you need me, I'm there. You just need to unpause me, and we can figure it out together. Well, let's begin. Our first problem. Find the area inside the bean shape. So sort of like this strange looking shape here. R squared equals sine theta plus cosine theta. Okay, well, it doesn't sound so bad. Now, what do we know? Well, we know our formula for area. We're going to see this a lot. What's area? Area is adding up starting angle to ending angle, 1/2 r squared, well, d theta. Oh, we'll just put an r squared there, right? So you have to figure out, okay, you always have the half. You need to figure out what's the right r, what are the right angles. So in some sense, it's pretty straightforward for us. In fact, we say r squared, perfect. We already know what r squared is. So this whole expression, r squared, is going to simplify to become sine theta plus cosine theta. So the only thing left for us to do before we do the integration is the angles. So we have to think about it. What is the right choice for alpha and beta? Now you might say, well, why don't we just go 0 to 2 pi and capture everything? The thing is that polar curves can be kind of strange. And sometimes you might feel like 0 to 2 pi captures everything, and it usually will, but sometimes it captures everything twice. What? So you have to be careful. So I strongly recommend that you don't just blindly say 0 to 2 pi for all the integrals, but rather think about the setup. Now, for us, when we see a shape like this, you might say, well, how do you figure out the bounds? Well, the answer is look for where you come in and out of the origin. That will tell you what you should be doing for your bounds. So for us, we say, okay, when do we hit the origin? Well, that's the same as saying when does r equal 0. So sine theta plus cosine theta would be 0. All right. Well, we can rearrange things. Sine of theta is negative cosine theta. And divide. That's the same as saying tangent of theta has to be negative 1. Okay, so see, the reason we wanted to divide is we wanted to get to 1 theta, a single theta. So then we could solve. Well, what's arctangent of negative 1? Now we know arctangent of 1 because we see it so often. Arctangent of 1 is pi fourths. Well, arctangent, it's a bit of an odd function. So that means that arctangent of negative 1 would give us negative pi fourths. So that would be this angle coming here, negative pi fourths, right? Okay, that seems to mesh with our picture. But remember, tangent is pi periodic. So to get the next time, you would add pi to it, and that would get you to 3 pi fourths. And that would be this angle over here. So we say, okay, that seems to agree with our picture. You can always have the picture for reference. So you should check, does this angle make sense in terms of the picture? And if the answer is yes, then it's like, okay, I'm probably doing it right. Good. And if the answer is no, check your picture, check your work, because something seems to be amiss. Well, so now we know what to do. We have the integral from negative pi over 4 to 3 pi over 4 of 1/2 sine theta plus cosine theta d theta. Well, that's an integral we can do because we know the integrals of sine and cosine. So you get 1/2 the integral of sine, negative cosine. The integral of cosine is positive sine. And we're going to evaluate from negative pi over 4 to 3 pi over 4. Now, the only thing that's challenging that's left is evaluating it and knowing your angles. Now, if you use the calculator, okay, sure, that can do it. The other thing is just to think, well, really it's the same as like cosine of pi over 4 and sine pi over 4, but with sign changes to keep in mind. So, with sort of that setting, if I think of 3 pi over 4, I'm over here in the what we might call the second quadrant. Cosine is the x value, so that's negative. Sine is y value, so it's positive. So what we would have is we would have 1/2, and we'd have minus, and the cosine. Normally, if just pi over 4 is root 2 over 2, so it's going to become minus root 2 over 2. Sine of 3 pi over 4 will be equivalent to sine of pi over 4, so that's root 2 over 2. Okay, and then minus 1/2. And when we plug a negative pi over 4, we're in the fourth quadrant. Here the x values, which correspond to cosine, are positive. Y values are negative, which means the sine values are negative. So we would have negative root 2 over 2. So in other words, it's the same thing as just cosine pi over 4. For sine pi over 4, it would be the opposite sign. So plus a negative root 2 over 2. Well, if you're careful with your signs, and you see, lo and behold, those signs can cancel. This minus sign distributes, so that everything becomes positive. Root 2 over 2 plus root 2 over 2 makes this a root 2. Of course, you have to times it by 1/2. Here, you have root 2 over 2 plus root 2 over 2, which makes that root 2. We have to times it by 1/2. But now you have root 2 over 2 plus a root 2 over 2, giving us a grand total of square root of 2. And we're done. That's it. That's it. Okay. So it all worked out fabulously. Great. Well, now let's go and try some more problems. Because the more that we do, the better that we become. And that's our goal, is to become better. And someday we'll be comfortable seeing all sorts of problems. We'll be like, this is just fun. That's where we want to. We want to get to the point where we see a problem and be like, fun? Okay. Are we there? Well, maybe not yet, but okay. Let's see what we have. Find the area of the region with x greater than or equal to absolute value of y, and bounded by the polar curve r equals root 2 secant theta plus tangent theta. And there's a picture below. Now, one of the things that sounds strange is you say, wait a second, hold on. I thought we were doing polar. What's this part here doing in a polar problem? X greater than or equal to absolute value of y? Sounds pretty Cartesian to me. Well, okay, so what's going on? What we're doing is describing a curve, and you can describe a curve in either coordinate system, and we can just say, look, we'll just figure out what that means. Now, we're used to y equals the absolute value of x, which forms that V shape. So when we talk about x equals the absolute value of y, it's like we're taking that V shape and turning it sideways. So this is the x equals absolute value of y, and then we would shade it. Now what we want to do is think about, okay, we want to switch everything into polar. How do we do it? Let's think about just this piece right here. How can we describe that in polar? Well, that piece right there, that's like the line y equals x, right? Okay, so if that's the line y equals x, what is it translating to? Well, that's coming out at like a 45-degree angle, or, since we like calculus things, we use radians, this really is theta equals pi over 4. In a similar way, this one down here, well, what's that one doing? Well, it's kind of doing the opposite, right? It's going downhill, right? It's going down. Well, for that, what happens? Well, that's coming out y equals negative x, and that would be at an angle of what? Negative pi over 4. So we can transform this statement, x greater than or equal to absolute value of y, to saying, oh, we're in between two relatively nice angles, pi over 4 and negative pi over 4. And then the last curve, it's already given to us in polar, and so we're happy with the last curve. That's great. So this piece right here, that's our r equals root 2 secant plus tangent. And now we say, okay, we can see what's happening here. What's going to happen is we're always going to go between our two angles, negative pi over 4 to pi over 4, and then we're going from our center out to this other curve. So this is great. We can set up this integral pretty straightforward now. So we get our area is integral alpha to beta 1/2 r squared d theta. Okay, that's just our generic form, right? Okay, now we clean it up. Well, our beginning and end angles are negative pi over 4 to pi over 4. This one, there's no symmetry. There's nothing we can do. We just got to do it all. That's okay. We don't mind. We don't mind. So, integral negative pi over 4 to pi over 4. Then we have the 1/2, and then we square that expression. Root 2 secant theta plus tangent theta squared d theta. All right, well, let's continue on, right? So we square. Okay, well, what does that give us? Integral negative pi over 4 to pi over 4, 1/2, and here we'll square the first term, 2 secant squared. All right, we have the cross term, so that's 2 root 2 secant tangent. And then we have the last term, tangent squared. All right, so that's our integral. Now we really have three pieces here. Let's talk about each piece. In other words, are we happy or do we want to think about it? Well, the first piece, secant squared, that's on our list of 10 integrals. So this is we're happy with this one. The next piece, secant tangent, aha, that also made the cut. So, again, we're pretty happy. Tangent squared, we're not quite enthused yet. Tangent squared is not on our basic list, so we have to do something with tangent squared. So the idea is, well, let's rewrite it in something that we can do. And for this, we say, oh, there's a nice relationship between secant and tangent. More particularly, there's a beautiful relationship between secant squared and tangent squared. So what we can do is we can say, you know, tangent squared is the same as secant squared minus 1. That comes from our identity, tangent squared plus 1 equals secant squared. So what do we get? Well, we get the following. Okay, so we're going to put the pieces together. We have a 2 secant squared and a secant squared, so that gives us 3 of them. Don't forget the half, so we can write this as the integral negative pi over 4 to pi over 4. We'll have 3/2 secant squared. Then a half times 2 root 2 will give us a plus root 2 secant tangent. And then there's this minus 1. We shouldn't forget about that. So minus 1/2 d theta. Now all our pieces are straightforward things we can integrate, so we're ready to integrate. Integral secant squared? Yeah, it's tangent. Okay, good. All right, just checking. All right, we want to be honest, right? Okay, so we have, this is 3/2 tangent theta. Integral of secant times tangent, secant. So plus root 2 secant theta. And then the integral of a half is a half theta. Don't forget the minus. And now we're going to go from negative pi over 4 to positive pi over 4. Okay, good, good. Well, let's see what happens. So when we plug things in, we get the following. So plug in pi over 4. Tangent of pi over 4 is 1. So we're going to get 3 halves. Secant of pi over 4 is, do you remember? It's square root of 2. Think of cosine. Cosine of pi over 4 is root 2 over 2, but it's also the same as 1 over root 2. To go from cosine to secant, we flip it over. So secant of pi over 4 is root 2. Root 2 times root 2 gives us a 2. Then you plug in minus a half times pi fourths, so that's minus pi eighths. Subtract, plug in negative pi fourths. Tangent of negative pi fourths is negative 1, so minus 3 halves. Secant of negative pi fourths, secant is an even function, and so what will happen is it's still the same as secant of pi fourths, so it's still root 2. So root 2 times root 2 will be a plus 2, and then we're going to have minus a half times minus pi fourths will give us plus pi eighths. Now from here, we're almost done. We can say, well, the 2's cancel because you have a plus 2 and this minus makes out a minus 2. Okay, so they were gone. Well, what isn't gone? Well, you have the 3 halves minus a minus 3 halves. Well, you can combine them together. So that gives us 3. Then you have minus pi eighths, because remember, this minus sign goes through to both the terms, right? So that would be minus pi eighths would be minus pi fourths. And there we go. Now, one thing you can check is the answer positive? Because we're talking about area. Area is a measurement, and therefore, when we finish, we should end up with a positive value. And this is positive. And you can also say, is it somewhat reasonable? And like if we got like 1 billion, we'd be like, that does not seem reasonable given the kinds of parameters. Now that we've gone through at the end, we probably could have said, we could have maybe saved ourselves a little tiny bit of work. And here's sort of the observation to make is you could say, look at our bounds. Negative pi over 4 to pi over 4. These are even on both sides, right? We go, pi over 4 in one direction, negative pi over 4 in the other direction. So we can look for symmetry. This part, you have an even function times an odd function is an odd. The other two are even. So what's going to end up happening is that the odd part will end up going to 0. And that's what happened. That's where the 2's canceled because you had an odd function that was coming from. And the even parts would end up doubling. And that's what ended up happening. So we could have said, I see I can separate into even and odd. I'll cancel out the odd part. I'll double up the even parts and go from 0 to pi over 4. Of course, that's all in, retrospect. But in the heat of the moment, I think we did pretty well. So there we go. All right. That's kind of a fun problem. Well, they're all fun, right? And the further we go, the more fun things become. On to our next problem. All right. Find the area inside the unit circle and outside r equals 1 minus cosine theta. And look, they're even nice. They drew our picture for us. So r equals 1 minus cosine theta, we saw that when we talked about graphing polar curves. And that had a name. It was called the cardioid. So that's this curve here. So it kind of looks a little bit like a heart if you turn it sideways. So that's why they call it the cardioid. So we'll just mark that. R equals 1 minus cosine theta. Now, we need to be outside of that. But we also need to be inside the unit circle. Okay, so we can see the unit circle here. We need to rewrite the unit circle in terms of polar coordinates. So what is the unit circle? Well, if you think of our coordinate system, the unit circle, it's all the points which are distance 1 away from the center. If you think as r, that's being the distance from the center, that means the unit circle is r equals 1. Great. Good. Now we have both the curves in polar coordinates, so this is progress. and we can start to think about, well, what's happening? What do we do? Well, we want to figure out our various bounds. That's probably the next thing. We could just look at the picture, right? And say, oh, I see the bounds. They're right there. This would be, up at the top, would be pi over 2. And I'll just mark theta. Down at the bottom would be negative pi over 2. Now, what if we didn't have such a nice picture? You can imagine that you might not have a great picture. In that case, what you would do is the following. You would say, well, set the curves equal. 1 minus cosine theta equals 1. Well, that tells you cosine theta has to be 0, which would tell us that theta would have to be some version of pi over 2. Positive pi over 2, negative pi over 2. We could go even crazy and say, well, 3 pi over 2, 5 pi over 2, 7 pi. There's lots of them. But for us, we see, okay, pi over 2 and negative pi over 2, those are our two bounds. In fact, things get a little bit better. Notice what our picture is indicating, that we have symmetry. In other words, you can imagine coming in, lifting it up, turning it over, and putting it back down. It would be the exact same picture. In other words, you have symmetry here across the x-axis. You can verify it directly from the functions you have, but it's also easy to see from the picture. Now, why do we like symmetry? Well, in many cases, it reduces the number of steps. But one of the things I like to use symmetry for is if I can get 0 involved, I love to get 0 involved because 0, it's so beautiful. So let's use symmetry and only do half of our problem. So let's go from theta equals 0 all the way up to pi over 2. So now we have sort of an idea of where we want to go. So in particular, our goal is we're going to find this piece up here, and then we'll double. All right, great. So where do we begin? Well, let's think about what's happening. So our area, we're going to double, because we're only doing half and doubling, going from 0 up to pi over 2. And then we're going to have another factor of a half, because that's the formula. Remember, whenever you do formula for area and polar, it's got to have that factor of a half. Now, in this case, it's an area between curves. So we should take a second here and make sure we know which curve is the inner curve and which curve is the outer curve. Sometimes it's not so obvious, and the way you do it is you always say, well, let's start off from the origin. And we go, whichever curve we hit first, that's our inner curve, and then we keep going. Whichever curve we hit second, that's our outer curve. So our furthest one out is the unit circle. So that will be the first term. So 1 squared, big radius squared, minus the inner curve, the one we hit first, 1 minus cosine theta squared, d theta. So big radius squared minus little radius squared. All right, great. Now, where to? Well, the 2 and the half, they cancel. Okay, yeah, that's great. Wonderful. That's progress. But in fact, there's more progress that can be made. So let's sit down and sort of work through what we have here. Let's clean up. Indeed, a lot of the work here, there's two parts. There's one is the setup, and the two is simplify so you have something you can integrate, which often involves algebraic expansion and trig identities. So for us, we say, okay, well, 1 squared, that's easy. 1 minus, okay, now square this term. 1 minus 2 cosine theta plus cosine squared. Okay, so far so good. We say, hey, more cancellation. The 1's cancel. They do cancel. Ah, fantastic. Okay, so what do we have? Well, what we really have is, don't forget the minus, so it's 2 cosine theta minus cosine squared theta, because that minus goes all the way through. And the 2 cosine, beautiful, we're happy with it, life is good. cosine squared could use some work. So what do we do with that? Well, we say there's a double angle identity. So this becomes the 2 cosine theta minus, and cosine squared is 1 plus cosine 2 theta over 2. All right. So that's what we have. Of course, we can simplify it. So this is really 2 cosine theta minus a half minus cosine 2 theta over 2. All right, so there's our inside, as simple as we could reasonably hope for. Indeed, so simple that we probably can actually do the integral. That's a good sign. That's a great sign, actually. We like it when it's that simple. So let's see what we have. This is integral 0 to pi over 2 of, and I'm just going to copy it down again, 2 cosine theta minus a half cosine 2 theta d theta. All right, well, we can integrate that. Integral of cosine would be sine, so 2 sine theta, then minus a half, well, that's minus a half theta. Here, minus a half cosine 2 theta. The integral of cosine is sine, still hasn't changed. But we have to account for that 2 on the inside. The way we account for the 2 on the inside is we would divide by 2. Well, we already have a half, so if we divide by 2, that'll get us to a fourth. So 1/4 sine of 2 theta. Evaluate from 0 to pi over 2. All right, well, let's see. Sine of pi over 2 is 2. So we have 2. Then a half times pi over 2 would be minus pi fourths. All right, and then here we have a fourth times sine of pi. Sine of pi is 0. Oh, great. Now what? Well, plug in 0. Sine of 0, 0. Here, 0. Here, 0. It all cancels. Wonderful, wonderful. And so, what do we have? Well, what we're left with is 2 minus pi over 4. And that's the answer. All right, great. Now, you might say, can we check it? Well, it's positive. That's good. There's actually something you could check. You probably would want to use your calculator for this, is to say, well, look, I can compute an area that's bigger than it pretty easily. Notice if we just took the half circle, what would that area be? Well, the whole circle would have area pi. Half a circle would have area pi halves. About 1.57 is what it would translate into. So this better be smaller than 1.57. And the good news is, well, if you take pi over 4, that's 0.75 something, I think, 0.76. You know, it's not very big. Not very big. And so it is smaller than pi over 2. So that's also a good sign. You know, you like to check that your answers are reasonable, because after all, we should be reasonable. That's one of our goals. All right, well, good. Let's keep going. And so we'll do another problem, almost very similar. Find the area inside the unit circle, inside the unit circle, centered at 1, 0, and outside the unit circle, centered at 0, 0. So we have 2 unit circles. The difference is one of them has been shifted over. Okay, all right, great. So it's kind of like you can imagine that you have like a planet or something, and there's a moon behind it, and you might be thinking to yourself, that's no moon. Well, you could imagine it was, right? Okay, now, one thing that might pop out to you is to say, whoa, hold on. There's no polar in this problem. Why are we doing this? Well, it isn't described in polar, but we can use polar coordinates to do the problem. Indeed, circles are a really clean description in polar coordinates, so oftentimes it's a great way whenever we have something like a circle involved. So let's think of these circles. Now, one of them is really easy, namely the circle centered at 0, 0, radius 1. What we normally think of when we think of the unit circle, that's the unit circle we think of. And this one we can describe as r equals 1. All right, great, beautiful. Now, what about the other one? Well, we got to think about this one. So, what's going on? It's a circle. In fact, we can't see the other side, but it comes down in some way. And I say, well, it's centered here at 1, 0. Now, maybe we don't jump right to what it is in polar yet, but we can probably write what it is in Cartesian without too much effort. So this would be x minus 1 squared plus y squared equals 1, because the center is at 1, 0, radius is 1. Now, let's clean this up. This becomes x squared minus 2x plus 1 plus y squared equals 1. And now we say, well, look, there's a lot of things you can do. You can cancel the 1s. All right. You don't have to make the noise, by the way, when you cancel. But if it helps you. All right. And we can say, look, this is the same as x squared plus y squared is 2x. And now we're like, wow, x squared plus y squared, very clean to convert to polar. That's r squared. And x, that's r cosine theta. Or we get r equals 2 cosine theta. So that's this curve. So that's actually not so bad. So they both have nice descriptions in terms of polar coordinates. Now we say, okay, what can we do? Well, as we've seen in other problems, this one has symmetry where you can imagine you come in, pick up, turn it over, put it down, the same shape. So let's say, look, let's take advantage of symmetry and let's go from 0 out to this point right here. That will be where we need to go, and we'll just double that result. Now, of course, that still leaves the small little question, all right, what's our other angle? Now it's maybe not so immediately obvious what it should be. We hope it's a nice clean angle. So how can we find that? Well, one way to find it is to think about what would be true. We need to have where the curves intersect. So that would happen when 1 equals 2 cosine theta, which is the same as saying cosine of theta is a half. And, well, of course, we all know our trig tables, right? When does cosine of theta equal a half? Well, you might remember it as 60 degrees, but we're in calculus, so that's at pi thirds. And now you can kind of look at the picture and say, does that make sense? Does that look closer, 60 versus 30? Because you might say, well, it's either 60 or 30, right? And you say, well, look at the picture. Does it look more like a 60-degree angle or a 30-degree angle? And you say, okay, yeah, it's a 60-degree angle. In some sense, we can also figure out that the cosine theta should be a half because there is kind of a beautiful symmetry going on here, where if you look at it, you would say, oh, okay, if you were to sort of flip the picture here, the two circles would just interchange so that the intersection happens at the x equals a half mark. So that's why we're not surprised to see cosine theta equals a half. All right. Well, we have almost all the players on the field. Let's write down what we have. So our area, we're going to double, because we're just going to do the top half, integral 0 to pi over 3, because remember we found that angle. That other angle of intersection happens at pi over 3. I guess we should mark equals theta. All right, good. So what comes next? Don't forget the half. 1/2. And now, well, in here, it's an area between curves. Now, one of the things that hints it's an area between curves is because we don't start right at the origin. We have to sort of go out a little bit first before we begin. So for us, we say, okay, how do you figure out the inner versus the outer? Well, start at the origin and just move out. The first curve you hit is the inner curve. The last curve you hit is the outer curve. So you think of the last curve as the big radius. So that would be the 2 cosine theta. So we're going to take 2 cosine theta squared minus the first thing we hit. That's our unit circle center at the origin, which has r equals 1 squared. All right, so there's our setup. Well, simplify. Now some things are pretty simple to simplify. The 2 and the half cancel, that's good. Another nice thing about using that symmetry. Well, what else? Let's see what we can write. This is the same as 4 cosine squared minus 1. Okay. Well, minus 1, fantastic. 4 cosine squared, not so much. We're not really feeling it yet. But we say, look, the problem with cosine squared is the power. If we could just find a way to reduce the power, life would be good. So we say, look, there's wonderful tools to reduce power. There's identities for it. Power reduction. So we can say, look, this is the same as 4 times cosine 2 theta plus 1 over 2. Or you could say 1 plus cosine 2 theta, whichever way you memorize it. It's all good. Well, what does that become? If we multiply the 4 through, so we'll get 2 cosine 2 theta, then plus 2 minus 1. So that'll be plus 1. All right, so that's what we have to integrate. Well, that doesn't seem so bad at all, because it's not so bad at all. So we have the following. This is equal to integral 0 to pi over 3, 2 cosine 2 theta plus 1. All right. Well, the integral of cosine is sine, but remember we have to account for the 2 on the inside. The way we do is divide by 2. There's already 2 there, so that becomes simply sine of 2 theta, then plus theta. Evaluate 0 to pi over 3. So we have sine of 2 pi thirds. All right, what can we say about sine of 2 pi thirds? Do you know it? It is square root of 3 over 2 plus theta. So that's pi thirds. And when we plug in 0, sine of 0 is 0, and 0 is 0, and so there's your answer. Now you might be saying, wait, how do we know that sine of 2 pi thirds is root 3 over 2? And if you're having a hard time seeing that right away, one of the things that you should do is think about, well, what is true? If we think about our unit circle, then pi thirds, that's our 60-degree angle. That's this angle coming up. 2 pi thirds is just straight across. So they have the same height, which means that their sine values are the same. So if we know what the sine of pi thirds is, we know what the sine of 2 pi thirds is. They're equal to each other. How do we know the sine of pi thirds? Well, we actually know the cosine of pi thirds was a half. That's how we figured out our angle. And so that means that the sine of pi thirds has to be, square root of 1 minus a fourth, which becomes square root of 3 over 2. Okay, however you choose to remember it, just remember it. That's good. You'll see a lot of things with trig. So this is a great chance to really brush up on our trig. So isn't it great? Trig is wonderful. One of the best ways to become good at trig is teach it for 2 years. That's how I became good. I'd recommend it to anybody. It it's a pretty big commitment, right, to go for 2 years, but at the end, at least you know a trick. Okay, here we go, our next problem. Find the area inside the curve r equals 2 sine theta plus sine 2 theta. And that's the picture. It's kind of an interesting picture. Maybe not what you would expect if you just heard the function out loud. It almost looks more like a heart than the cardioid does. Well, that happens. Now, what happens when you actually go through and map this curve? Well, the way the curve goes is it does the following. So it starts off at 0, and then it comes along and goes out, and then here is pi over 2, and then it comes down at pi. Now, at pi, you can see you're back to the origin because you get sine of 0 is 0, sine of 2 pi is 0. And then what happens is you go negative. And so, even though it looks like, well, shouldn't you be down here? Because you're negative, you're from pi to 2 pi, you're looping up here until we get back to 0 again. Okay, so that's sort of the process. It kind of loops and it has this intersection going on. Now, how do we find it? Because you might be thinking, well, what if we just did 0 to 2 pi? If you did 0 to 2 pi, that would be a not great idea. Why not? Well, if you did 0 to 2 pi, what would end up happening is that this region here would be counted twice, whereas these two regions would be counted once. So you definitely would have the wrong answer. And it's not just as simple as, oh, I just need to divide by 2. No. That over-counting in the overlap says you do not want to go from 0 to 2 pi. You might say, okay, well, look, I'll just do 0 to pi. Well, the problem is if you do 0 to pi, you're not going to get half the shape. You're going to get sort of like this egg piece here. But you can't just double because there's, again, this little overlap. So what do we do? Well, you probably can see what we should do. What we can do is say, look, let's go just 0 to pi over 2. So if we do that, then we'll capture that part, which is exactly half. So, aha, now we have a plan. So we'll go from 0 to pi over 2 straight up. But that's going to be half the shape, and you can see that if we lift it up, turn it over, put it down, we'll get the other half as a freebie. So now we have our plan. Our area will be doubling, going from 0 to pi over 2. Don't forget the half. And here, we're just going straight out. See, we're not going to this inner part because this inner part doesn't happen until later on. That part right there is from pi to 3 pi over 2. From 0 to pi over 2, that's this curve here. So we're going out from the center to that curve. So this is not between curves. So it's just the r squared. All right. That's wonderful. We're doing great. Now, we just have to simplify. Well, a little bit is pretty simple. 2.5. Okay, that's easy. Great. Now, let's go through and see what this becomes. The majority of the work on this problem is really just saying, I have a trigonometric expression. How do I rewrite it as a trigonometric expression I can integrate? Because not every trigonometric expression is directly integrable. But when we treat it gently, kindly, with a bit of love, we can succeed. So let's square. So what would we have? We would have 4 sine squared plus 2 sine theta sine 2 theta plus, not 2, because there's a 2 there, So we'd have double that. So that's 4. Sorry. Good to check, right? A squared 2ab. So that's why that's a 4. And then plus b squared, sine squared 2 theta. Well, let's talk about each piece. Now, are we happy with the sine squared of theta at the beginning? No. The problem is it's sine squared. If it was sine, happy. Sine squared, not happy. So what do? Well, we use power reduction. Say, okay, that's not so bad. We can do something here. So this part, this first part, would be 4. And then we would have sine squared is 1 minus cosine 2 theta over 2. Okay, that's great. While we're at it, notice the sine squared 2 theta at the end. Okay, more power reduction. Now, what do we do here? Well, the same thing, right? 1 minus cosine of, now there's a dramatic pause, almost to imply something interesting happens. When we're doing power reduction, we double our current angle. Our current angle is 2 theta. So when we double that, we'll get 4 theta. So there will be a 4 theta there. Now, the middle term. What do we do for the middle term? If you look, what do we have? We have sine theta, sine 2 theta. It's like apples and other kinds of apples. Really, the problem is that the insides aren't matching up. One of them looks like theta, the other one looks like 2 theta. We really want them to be looking the same. So how do we do it? Well, there's a couple things you can do. If you know a lot of trig identities, you can say, oh, sine alpha, sine beta, there's a way to rewrite that in terms of cosine. If you remember that, that's great, good for you. But I try to remember relatively few, and one of the ones I do remember and I find very helpful is double angle. So I can replace the sine 2 theta by 2 sine theta cosine theta. There's already 4 there, so that would make this 8, because there's a 2 coming there. Then there's a sine, and there's a sine, so that's sine squared. And then there's a cosine. Now, at this point, you're probably like, now you've got apples and apples, but you've got to have a sine squared. Don't you need to do something else here? Not yet. We'll get into that in a little bit. Okay, so let's see what we have. So we're going to clean this up. So we're going to be really careful here. So what do we have? We have, this is integral 0 to pi over 2. So let's see what we have. We have 4 over 2 makes 2 plus a half. 2 plus a half, also known as 5 halves. Okay, that's not so bad. Then we have minus 2 cosine 2 theta. Then we have minus a half cosine 4 theta. And then this last piece, 8 sine squared cosine theta. Okay, well, let's integrate term by term. So we have 5 halves theta, all right. Here, integral of cosine will be sine. And then, because of the 2 on the inside, we need to divide by 2. There's already 2 there, so sine 2 theta. Here, the integral of cosine is sine. But then we say, look, we've got to divide by 4. There's already half there, so that makes it a 1/8. Now this last term. How do we integrate 8 sine squared cosine? Well, the way we do it, we're actually going to do it in our head, is that we see, oh, there's a perfect substitution to make. Because the derivative of sine is cosine. So if you set u equals sine, then this would become your du. So what we really have is 8u squared. How do you integrate 8u squared? Well, you would have 8/3 u cubed. And then just remember, well, u is the sine. So we did a substitution in our heads. That's how we did that one. All right, so we're almost done, except for, of course, the one small detail where we have to evaluate from 0 to pi over 2. And once we do that, we really will be done. So let's see what we get. When we plug in pi over 2, 5/2 times pi over 2 is 5 pi over 4. 2 times pi over 2 is pi. Sine of pi is 0. 4 times pi over 2 is 2 pi. Sine of 2 pi is 0. Sine of pi over 2 is 1. If you cube that, you still have 1. So plus 8/3. Plug in 0, you get 0. And sine of 0 is 0, so all those terms are 0. And therefore, we're done. 5 pi fourths plus 8/3. Wow, what an answer. What a great answer, really. It's kind of cool. Probably not the one we would have expected, but it's the one that worked out, and that's all right. Great, beautiful, beautiful problem. So let's keep going, right? Well, our next problem. Find the area outside the unit circle and inside r equals 2 cosine 3 theta. And they shaded it for us so that there was no ambiguity about what they wanted. See, there's these 3 pieces here. So this is the 2 cosine 3 theta. It wraps around as you move around. Now, it kind of has this sort of strange phenomenon where if you went from 0 to 2 pi, it would actually wrap around twice. But that's another story for a different day. But we see, it doesn't make sense to compute each individual petal because they're all the same shape. So we say, okay, look, instead of doing 3 integrals, let's just do 1 integral and triple. Okay, that sounds like a great cost-saving measurement. All right, so we have our area will equal 3 times something, right? Because we're just going to do 1 petal. But actually, let's go even further and say, hey, look at this first petal. I could split it in half. And then if I just do this top half, I could double, and that would give me the area of that petal. So we say, great, we're going to double that. So we're going to double going from 0 to something. Okay, so now we actually have to think, where do we go? What's the right angle? So for this, we have to pause and sort of say, well, that's at where the 2 curves intersect. Now we know the unit circle is code for r equals 1. So we say, all right, we want to know when does 1 equal 2 cosine 3 theta. And of course it's going to equal 2 cosine, they're going to intersect many times. Every time that these curves cross, that's a solution. So it's multiple times. We just need the first one. Okay, well that says the same thing as saying cosine of 3 theta is a half. All right, now don't worry about the 3 theta part yet. Do we know an angle where the cosine of that angle is a half? And if we do, what is it? Well, yeah, we do know an angle where the cosine gives us a half. It's 60 degrees, also known as pi thirds. So now we say, okay, cool, pi thirds, right? And you're looking at the picture and say, no, pi thirds would be up there. You got it wrong, Steve. But wait, pi thirds is what we need to plug into cosine to get a half. Remember, what are we plugging in? We're not plugging in theta, we're plugging in 3 theta. So 3 theta should be pi thirds, or theta should be pi ninths. You might be getting a little bit nervous and saying, I'm not comfortable with the angle pi ninths. but keep going with it. Oftentimes, if you have a strange angle, what will happen is when you come to the evaluation, you'll scale it by an appropriate amount, and it'll be, oh, these are angles I am comfortable with. Things worked out kind of nicely. So we keep going. So we're going to go from 0 to pi over 9. Now, what comes next? The half. Don't forget the half, right? We want to make sure we always remember to put that in. So 1/2, and now it's an area between curves, because we can see as we come out, we're not hitting anything, we're not hitting anything. And then we hit a first curve, we hit our region, and then we hit an outer curve. So the further curve, the one that's furthest out from the center, is the 2 cosine 3 theta. So we'll have 2 cosine 3 theta squared minus the inner curve is the unit circle, radius 1 squared. All right, there we go. Once we find that, we're great. So let's get to work. Now, one of the things we can see, the 2 and the half cancel. 2, great. All right, now what else can we do? Well, let's work on the inside part, the thing that's inside the integral, and see if we can't simplify it. So this would be 4 cosine squared 3 theta minus 1. The cosine squared, that's we need to use power reduction on. So this is 4 times 1 plus cosine of something over 2. Be careful here. So we're doing power reduction, but the inside is 3 theta. So when we do power reduction, we're going to get to twice that, so that's 6 theta. So that's 6 theta there. And now we say, great. Well, notice what you have. 4 over 2. Well, that really makes this a 2. And you have 2 minus 1. So we have that this becomes the integral. We have that 3 out in front we're not going to forget about. Integral 0 to pi over 9. And we have 2 minus 1, which is 1, plus 2 cosine of 6 theta. Okay, great. We've got our problem set up. Not only do we have it set up, we did that a while ago. We have it simplified to the point we can actually integrate. So, what do we have? Well, this is 3. Then we have theta plus, now the integral of cosine, positive sign, but we need to account for the 6 on the inside. We do it by dividing by 6. 2 divided by 6 makes us a 1/3. And we go from 0 to pi over 9. So, almost there. Plug it in. We get 3 times pi over 9 plus 1/3 sine of 6 times pi over 9. Well, that's the same as 2 pi thirds. Now, when you plug in 0, you'll get 0. Sine of 0 is 0. You're done. Now, we're almost finished. Well, we just need to know a few things. 3 times pi ninths, well, that's really right as 1/3 pi. Now, 3 times 1/3 cancels. Do we know sine of 2 pi thirds? The answer is yes. We actually did it in an earlier problem. Sine of 2 pi thirds, if you think of your unit circle, you say, look, pi thirds is over here. 2 pi thirds is directly opposite. They have the same height, so that means they have the same sine value. So sine of 2 pi thirds, which is sine of pi thirds, is the square root of 3 over 2. And we're done. That's it. That's it. That wasn't so bad. That wasn't so bad at all. We just, are working through our process. You're probably feeling like, okay, I'm getting the hang of this. I'm doing pretty well. Life is good. All right. Keep that attitude up. because we're going to do some more challenging ones eventually, right? Well, maybe. Let's do one more for right now. And we always have more practice later on, but one more to finish up. So, find the area inside both of the curves. So I have two curves. R equals 2 minus sine theta, and R equals 3 sine theta. Now, it doesn't tell you which curve is which, but I'm going to just go ahead and tell you which ones they are. You might recognize curves of this form, R equals something sine theta. Those are circles that are centered on the y-axis. So that's the top curve. R equals 3 sine theta. R equals 2 minus sine theta is this bottom curve. This kind of looks vaguely almost like a snow person, right? Where you have like big bottom part and sort of a medium part there. Maybe if you had another curve up there, we could really finish it off. So, what do we do? Let's talk about what this is and what this isn't. Is this a problem of finding area between curves? The answer is no, it's not, because we never go between two curves. Think about what's happening from the perspective of the center. So what's happening is as we go out, we see we're not going to be below, we're going to be above. So we're going to be going from this angle, theta equals 0, to this angle, theta equals pi. Initially we go out and we hit this curve. So for a small part, we go out and we hit the circle. Then we go out and we hit this other shape, r equals 2 minus sine theta, for a while until we hit this angle. And then we go back to a circle. So what are we going to need to do? Well, we could think of it as, well, I've got to find, this little piece down here, find this part up here, find that little piece and add them all up, and then we're good. So what we're going to do is something like that. But we want to save ourselves some work, because that sounds like we have to do 3 things. That sounds 3 times as much as we'd want to do. Can we simplify it to doing 2 things? Well, again, there's our symmetry. We could come in, pick up, turn over, put it down. We have the same shape. So we say, perfect. So what we can do is really think about it in 2 stages. There's this little tiny sliver of the circle, and then there's this other part up here. And if we can find those 2 pieces and then double, that'll give us the whole shape that we're looking for. All right. So that's kind of a plan. So we're going to have to do 2 integrals. This is good. All right. So we're going to get really good at doing these integrals, right? Well, yeah, that's what we need to do. We need to get good at doing these integrals. We can see a couple of our angles. We have our 0. We have also going straight up. That's pi over 2. So what's this angle? The last piece that we need to know is that angle. Well, let's work through it. So what needs to be true? Well, this is an angle where we need to have, we'll put it down here in this little corner, 3 sine theta needs to equal 2 minus sine theta. Well, you can add sine theta. That says 4 sine theta equals 2. Divide by 4. Sine theta should equal a half. All right, so that's what we need. Sine of theta equals a half. Do we know an angle where sine of theta is a half? We do. And I hope you do. It's, come on, I believe in you. Of course I do. Pi 6, also known as 30 degrees. And you can check, does it look like this is an angle of about pi 6? And it does look about that, so that's a promising sign. So now we have our integrals. So let's write them down. Again, remember there's 2 pieces, and then we're going to double each of them. So we're going to double the part from 0 up to pi over 6. And for that, you're going to have 1/2, because there's always a factor of a half. And we're going from 0 out to the circle. So 3 sine theta squared. Plus, we're going to double, and then we're going to do the integral from pi over 6 to pi over 2. And there's a factor of a half. Always remember that. And from there, we're going to go out to the other curve, 2 minus sine theta. So 2 minus sine theta squared. So that's the setup. Let's finish it. Let's go through and carry this out all the way to the end to see what we get. The 2 and the half cancel in both of them, so that's good news for us. In the first term, we have the 9 sine squared. Well, so we'll rewrite this part as 9, and the sine squared is 1 minus cosine 2 theta over 2. Here, we'll start by squaring. That's 4 minus the cross term, 4 sine theta. A squared minus 2ab, and plus sine squared. Well, sine squared, we know, we just did it. That's 1 minus cosine 2 theta over 2. So again, this is our sine squared. Sine squared. So what do we really have? We have integral 0 to pi over 6, 9/2 minus 9/2 cosine 2 theta d theta plus, here, what do we have? We're going to have the integral pi over 6 to pi over 2. We're going to have 4 plus a half, right? Because there's a 4 and a half, which makes this also 9/2. Oh, okay, that's interesting. Minus 4 sine theta, and then minus 1/2 cosine 2 theta. All right, good. We've now gotten everything to a point where all the pieces are ready for us to work. So let's integrate. This will be 9/2 theta. All right, that's the easy one, right? Integral of cosine is sine, but remember you have to divide by 2 because of that 2 there. So that'll be 9/4 sine of 2 theta. And evaluate from 0 to pi over 6 plus, going through here, 9/2 theta. Integral of sine, negative cosine. There's already negative, so plus 4 times cosine. Here, the integral of cosine is sine. It'll still be a minus. And we say, well, look, we have to account for the 2 on the inside, so we divide by 2. So it's really a 1/4 sine 2 theta. And we go from pi over 6 to pi over 2. All right. Well, let's hope nice things happen. So when we plug in pi over 6 here, we're going to get 9/2 times pi over 6. All right, 9/2 times pi over 6. Clean that up later. Then we have minus 9/4 sine of 2 pi 6, sine of pi thirds. Sine of pi thirds, we know, it's the square root of 3 over 2. Okay, so I'm just using that sine of pi thirds is the square root of 3 over 2. So that's that step. Plug in 0. Good news. 0 is 0, sine of 0 is 0. So that's that for the first integral. Second integral. Here we go. Plug in pi halves. So we're going to have 9/2 times pi halves, whatever that turns out to be. Cosine of pi halves is 0. Great. Sine of pi, because we have to double pi halves, also 0. So that's it for the pi halves. Now we have to subtract. Okay, so subtract. Plug in pi 6. 9 halves times pi 6, whatever that turns out to be, plus, then we're going to have 4 times cosine of pi 6. Well, what's cosine of pi 6? It is square root of 3 over 2. Right? So sine of pi thirds is the same as cosine of pi 6. They both equal square root of 3 over 2. They're actually, if you think about it, pi thirds and pi 6 are complementary angles. And if you think about the relationship between sine and cosine, is they have a nice relationship in terms of the complements of angles. So, anyways, we got that angle. Great. Good. Minus 1/4. Then we have sine of pi thirds. Okay, well, sine of pi thirds is what? Well, square root of 3 over 2. Again. All right. Now, we just have to group everything together and life will be good. Let's see what we have. Some good news. Some good news. Notice the constants. See that 9 halves times pi 6. Here's a 9 halves pi times pi 6. They're canceling each other. Gone. So, what do we have? Well, we have this piece. That hasn't canceled with anything. And it's certainly not going to combine with anything else. So, that's going to be part of our answer. So, that's 9 halves times a half is 9/4. I'm going to just put it up here. 4 pi. Okay, so we've now accounted for this term. So, this is done. Check. So, what else do we have? Well, let's see. We have here, this is a 9/4 times square root of 3 over 2. So I'll write this as a square root of 3. And here, I can think of this as negative 9 over 8. Yes? Right? 9/4 times a half. Here, I have 4 over 2. So if I want to make this over 8, I can make this 16 over 8 times by 4 over 4. And it's being subtracted. So minus 16 over 8. So that's this term. Plus, and here it would be minus minus, plus, and then 1 over 8. Well, that actually becomes not so bad, right? Minus 9 minus 16 is minus 25. Plus 1 makes minus 24. Divided by 8 makes this minus 3. So this makes this minus 3 root 3. So 9 pi over 4 minus 3 square root of 3. And we're done. That's the answer. Wow, what an answer. It kind of simplified pretty well, about as well as we could have hoped for at the end. And so this is a case where we had to be careful. It's like, okay, we were looking for an area inside 2 curves. So it's like, all right, so we got to break it up and say, when do we hit one curve versus when do we hit another curve? Use symmetry and work it out. Be careful. Be careful. And not so bad, right? We can do this. This is pretty good. Most of it comes down to, can we figure out how to rewrite trigonometry in a nice way? So keep at it. Keep doing the practice. And I'll see you again in a future session. Bye.